Slicing is the term used to describe the process of converting a piece of CAD geometry into a file which is capable of being executed by a 3D printer. The basic workflow involves using software to divide the CAD file into a series of 2D layers, each with a thickness that the 3D printer can print. These layers will be saved in a file type and sequence that the printer can build the part from. The CAD files for 3D printing are most commonly STL files, but most software accepts other file types, like OBJ. And recently the 3D printing industry has developed the 3MF file, which can store more information specific to 3D printing and the settings used in slicing the geometry. While 3D printers are capable of creating very complex forms, there are still factors that can affect the cost, speed, strength, and finish of parts. To make the most of the manufacturing process, users should think about the shape and use of the part. Firstly, this will help to choose the orientation, which is the position and angle that the part sits relative to the print bed of the machine. In the most common 3D printing methods, fused filament fabrication and vat polymerization, the print orientation affects the amount of support required during the printing process and the layer orientation relative to the part. Supports give place for the geometry with overhangs to print on, as it is impossible for many 3D printing processes to print in mid-air, or beyond certain overhang angles. These support structures are removed after the printing process, but can sometimes leave imperfections on the part that require future repair. As 3D prints have a layered structure, they behave very like they have a grain, similar to that of wood. If the part is loaded in a way that pulls the layers apart, it will fail, so choosing a suitable layer orientation can add to the strength of the part. Once the orientation has been chosen, other slicing settings need to be selected based on the print requirements. The layer thicknesses available will be dictated by the layer resolution that the printer is capable of printing. For example, a stock FFF printer will print from 0.05 mm to 0.2 mm. This can be changed by adjusting the extruder nozzle diameter. Increasing the thickness of the layers reduces how long the print will take, but results in visible lines on the surface of the print. On some objects, these lines are used as a design feature. On others, they're smoothed out using filler and sanding. With most 3D printing processes, it is possible to choose whether to create a hollow or a solid part. If choosing a hollow part, it is possible to set how thick the external walls of the part are. Thicker walls will strengthen the part, but increase the amount of material used and the time taken to print the part. It is also possible to partially fill the internal cavity of the hollow part with a fill structure. This is a repeating structure that adds some strength to the part, but again at the expense of the material used and the time taken to print. Once all of the settings have been applied in the software computes the information needed by the 3D printer to print the part. This is usually a G-code file. For FFF printers, the software computes the path that the print head will need to follow while extruding material to build each layer of the part. For LCD-based vat polymerization, the software computes the image to be displayed for each layer of the part and the movement of the print plate. The saved G-code file can then be exported to the printer, which will use the G-code to build the part.